Okay, I'm back with the um, model part, and let's start. So here we have done a lot in the dataset part, and we created our own dataset, and I'm so happy and glad. And now let's actually head over and create the model. But before we do that, let's actually import some dependencies. So creating, let's import, or let's say from TensorFlow dot press dot models import model from TensorFlow dot press dot models, or actually let's say import model and load model, and then let's say from TensorFlow dot press dot layers import dense layer on the 2D global max volume 2D and input layer, and then let's say from TensorFlow dot cross with applications import VGG16. And the reason I'm importing VGG16 is that because if we are going to use its weights, it's between weights on ImageNet, and there are good initialized weights, and it can help us improve our model, and that's it. So let's say VGG equals VGG16 and include top equals false. We don't want the end of the network value, end of the network layers. We don't want the dense layers in it. We just want the whole CNN architecture. So let's run this. And let's run VGG summary. And you can get a summary of its architecture, as you can see. And it's a really good architecture. And then let's create a function for building the model. So let's say define build model, and let's say input layer equals input for the shape equals 120 to 120 by 3, and VGG equals VGG16, include up equals false, and we're gonna say this goes to the input layer to connect the input layer in it. And let's do the bounding box part. Oh no, sorry, the classification part. Let's say F1 equals global max volume to D, and let's apply it on VGG. That is the first layer or the input layer, and then let's say class 1 equals the dense layer of 248 rounds, and the activation equals relay, and we apply this at 1, and class 2 is dense layer of 1 neuron, and the activation is sigmoid. And we apply this class 1. Then let's do the regression part. And let's see, F2 global max pulling 2D on VGG. Then let's say class 1 or say regression 1 fills a dense layer of 248 neurons and with the activation of real U, and this will apply it on a tool, and let's say regression 2 equals dense layer of 4 neurons because we have 4 values in our bounding boxes, and the activation is a sigmoid again, and we're going to apply this on regression 1. And then let's say base tracker equals model on input equals inputs layer, and outputs, let's fix the syntax here, and the outputs are the class 1 and class 2 on the regression, and let's return the base track. Now let's say base tracker equals build model. Then we're gonna say base what? Something is wrong here. Build model. No, this should be inputs. Yeah. Base tracker. That's summary. Let's have a summary of the architecture. Then we're gonna actually head over and make a prediction real quick, so we can test out some actually abilities, I guess. And let's say x and y equals train dot as numpy iterator dot next. So we get a batch and we unroll it to x and y. And then let's see the x of x that shape, that should be 8 by 120 by 120 by 3. Okay, that's 8 by 120. Okay. Let's say classes and the coordinates equals base tracker that predict x, and then let's say classes and coordinates so we can see them actually. That should be big X. And then as you can see, this is real nice. Okay, so let's continue. Now, actually, let's open up this. Okay, so here we can actually head over and make some variables that are necessary, the model. So let's actually say defining necessary variables. Okay, so let's say batches per, let's say batch per batch per epoch equals length of our train set. And then learning dk is 1 over 0.55 minus 1 divided by batch per epoch. Epoch. That's epoch. And let's say optimizer equals TF that plus the optimizers dot OKC dot Adam learning rate equal 1001 and dk is learning dk. And then define localization loss. Let's define the localization loss. That is the loss that computes the actual loss regression model. Let's say delta coordinates equals tf dot reduce sum tf dot square y true true, and then y hat true, and also we're gonna say nothing else. Now let's say h true. So here we're calculating the square difference between x and y coordinates of the true and predicted bounding boxes. Now let's calculate the height and width of the true bounding box, h through equals y through 3 here minus y hat 0 and 1. And then let's say w through equals y through 2 here minus y hat 0. And then let's say h predict equals y true for 3 here, but this should be y hat actually, minus y hat should be 1, right? Okay, and w predict equals y hat and 2 minus y hat 0. Okay, so now let's calculate, okay, and now let's calculate the square difference between the height and width of the true and the predicted boundaries. So let's say delta size plus tf that reduce sum for tf that square for w true minus w predict and tf that square for w for h true minus h predict, and let's return the delta size plus the delta 4. Okay, let's run this. And now let's define the classification loss to be f dot cross dot losses dot binary plus entropy, and the regression loss would be the localization loss. Okay, now let's define the model final class. Defining final model class. Okay. Okay, so let's continue and build up the model class. So let's define class name base wrapper. Let's say self and model. Let's say base tracker and key arguments. Then let's define the init function that takes the self, the face tracker, and sorry, I did something. It takes a model and let's define the init function. So the init function itself, base tracker, and key arguments, keylocks, and GPU super dot init locks, and then just do self dot model equals base tracker. Okay, now let's compile. Let's define the compile method. It's self optimizer class loss operations actual localization loss and you. And now let's say super dot compile for keywords, and we say self dot c loss or classification loss equals class loss, and self dot localization loss equals localization loss, and let's say self dot optimizer. Then let's define the train step that takes the same kind of batch and keywords. And let's unroll the batch, say x and y equals batch, and read tf dot gradient state dot add state. Let's say classes and coordinates equals to self dot model for x, and training equals true. Then let's say batch class loss or batch classification loss equals to self dot c loss for y 0th dimension. That means those 8 numbers in the batch and classes. Then let's say batch localization loss equals self dot L loss or localization loss for TF class and for y the one dimension. That means the coordinates that are predicted, and TF dot float 32 and the coordinates. Then let's say we want the total loss be batch localization loss plus 0.5 times batch class loss. Then let's say gradient equals tape dot gradient for the total loss and the self dot model dot trainable parameters. Then let's create the actually test the step function that do the exact same thing. Some things. And okay, now we should change some thing here. There's nothing to change actually, but we should set it to false and nothing anymore. And let's actually say return total loss equals total loss and class loss equals class loss and regression loss is actually need to be batch class loss. And regression loss is batch regression loss of batch localization loss. And let's say, okay, now here, let's also do this in here. And then let's do define solve first. All yourself and x and keywords. Now let's say return self dot model on x and key. Okay, now that we defined the model class function, the model class, we can actually head over and define the model and compile. So let's say model equals face tracker or the face tracker model that we defined above. And let's say model dot compile. Okay, face tracker. And now let's do this cell, this should work now. Now let's compile the model. So the model dot compile, this takes the optimizer, classification loss, and the regression loss. Okay, let's compile the model. Now, let's do ist equals model split main epochs equals 100 and validation data equals validation. Now let's train the model. Something is wrong here. There, in line 20 in train step. Okay, let me fix this. Okay, so that was a simple syntax error and nothing else. I wrote the correct thing here, and it's on epoch. I recommend you to do 100 epochs or even more. More is better, but I think this is good for this tutorial. And when the training is done, I will come. Iterator, and let's run this. On the server is data sample dot next, and let's copy the function for it so we can plot it. Okay, let's first make the prediction. Let's then plot the prediction. Now let's plot the prediction. As you can see, it's performing really good here. Performing completely alright and good. Now let's see the next batch. As you can see, it's performing really good. Let's get the next batch. Let's get the predictions and let's plot them. It's performing really good again. So now let's get the next batch. Don't need to run this because it goes and defines the data set again. So we don't need that. We just need to get the next batch prediction, plot them. So let's see. It performs really good. It performs all right and really good. And so you can save the model like this. Let's say base tracker save as, or we can say model, let's save. Maybe we can say model, let's say, and let's say base tracker dash 5. Okay, that's based on. Okay, then you can load the model like this. Let's say base tracker equals load model. This is the function we imported from Porsche TensorFlow that trusts that models, and can pass base tracker and that's it. And you can also download this And yep, I guess that's that's all. And if you like this video, please subscribe to my channel, like the video, and please give your opinions so I can record better tutorials for you. And thanks for watching and follow along this vlog. And thanks. Bye.